So I think we are complete. Sorry for the delay. We are a couple of minutes late. Hello, everyone, and welcome. I'm John De Gregorio, Head of Unit of Scientific Services and Cooperation at WIP Renewable Energies, and Conference Director and Scientific Coordinator at EU PVSEC. I'm really excited to kick off this first joint webinar between EU PVSEC and EASE and EU PVSEC. Thank you for joining. All the speakers, of course, and all the audience. We are pleased to welcome you all. We will be talking about how photovoltaics and storage are coming together to shape the future of energy and how our collaboration is helping drive that change. We have prepared an outstanding, in our opinion, of course, panel of experts who will share their perspectives and experiences with us. The agenda, most likely all of you have seen it already. I will share it. I hope you can see it. I will start with a short introduction, and the session afterwards will be divided in two blocks. One with 10 minutes presentations each, and one panel discussion that will be moderated by Jacopo Tosoni, Head of Policy of EASE. With us are today, let me introduce our panelists / speakers. Robert Kenny, Silvestros Vlachopoulos, Gracia Barki, and Ed McCulloch. I will introduce them more into detail once they are about to deliver their presentations. Just one side note: at the very end of the session, we will have a Q&A session. Part of the session. Don't be shy, all the audience, sharing your questions. Please do so in the section of Q&As, not in the chats, because it's currently not available. So let me start by introducing the company where I'm working in just 20 seconds. WIP is the organizer of the EU PVSEC and is a consultancy at the intersection of science, business, and policy in the field of renewable energy. We offer a broad variety of services that promote a sustainable energy future that can be summarized in the blocks that you can see on the screen. Just a quick intro. EU PVSEC is the world's largest scientific conference focused in photovoltaics. We bring together researchers, innovators, and industry leaders. And EASE is the leading voice for energy storage in Europe, advocating for smart, flexible energy systems. Together, we are bridging two, in our opinion, powerful sectors. So why this collaboration, you might ask yourself? Because solar and storage are no longer separate conversations. They are converging, and by joining forces, EU PVSEC and EASE are creating a platform for shared innovation, integration, and real-world impact. Our missions are perfectly aligned. EU PVSEC is all about advancing PV research and deployment, where EASE is more focused on making energy storage a cornerstone of the energy system. Together, we are working toward a smarter, more resilient grid. The energy transition is not just about clean power, it's about making that power reliable. PV gives us clean electricity and cheap, and storage makes that electricity flexible, available where and when it's needed. So it's the perfect match for a future-proof energy system. We are seeing a shift from PV and storage as separate technologies to fully integrated systems. This integration is what will power our resilient, decarbonized grid. So it's not just complementary anymore, it's essential. And the market is catching on. By 2030, more than half of new solar projects will include storage. Global storage capacity is expected to grow 17-fold. It isn't a trend, it's a transformation. The economics are changing too. PV plus storage is now cost competitive with fossil fuels. And you might ask, how about the global market? Well, it's projected to exceed $50 billion a year by 2030. This is really, really massive. And innovation is what's driving this forward. From better PV materials to smarter batteries and AI powered systems, the path of progress is amazing. And collaboration is what accelerates it. Looking ahead, we need unified planning across generation, storage, and the grids, and we need shared standards, shared skills, and shared goals. That was it from my side. A short intro. Thank you very much for your attention. If you would like to connect, partner, or just keep the conversation going, just reach out. After this short presentation, now we will introduce our first speaker of the day, Robert Kenny. I have here some words about his bio. I will stop sharing. Robert will be delivering short presentation on with title Snapshots of Photovoltaics in 2025. Robert is a senior researcher at Joint Research Center of the European Commission. His expertise lies in PV module measurement, tests, energy rating, and novel photovoltaic technologies. He plays an active role in international standards development and currently serves as technical program chair of EU PVSEC. Robert, the floor is yours. Thank you.
Thank you very much, John. And I thank also our colleagues from the ESE as well for the opportunity to talk today. I think it's a great opportunity, and also thank everybody who's joining us online now to follow this. So I'll try and be brief. The idea was to give a quick overview of what's happening in the world of photovoltaics from the perspective of the European PV conference. So it's my intention is not to go into details, but just to give a kind of overview of what's the main things that are happening and what's likely to happen in the next in the next short horizon, let's say, and particularly look at how these developments are also important, also in the context of storage. So the PV conference has started in the 1970s, supported by the European Commission, and the Commission maintains a strong support for this conference, and also the area of PV in general is very, very important to meet the European Union targets for net zero by 2050. So it's a fundamental technology, not the only one, but very, very critical to these targets. This year, the conference will be in Bilbao towards the end of September. So of course, we'd love to see some of you there if possible. So now, having said that, I will jump on to some bit more details of the topics. So that with the next slide, please. So the topics of the conference are five. The first one focuses on silicon materials and cells. The image there is really just for a little bit of decoration. It's an example of a cell structure. But it's nothing specific coming from this year's conference, just to be clear. Okay, so the silicon is still the #1 technology in terms of the market. More than 90% of the modules put out into the field are silicon, crystalline silicon based. So this is clear. However, on the other side, the technology has advanced so much over the years that we're now approaching the fundamental limits of what it is able to do. So the researchers are trying to squeeze out every fraction of a percent of additional efficiency, and they're working on new designs to do this. So you hear the words such as TOPCon, heterojunction, IBC. These are technologies which are being looked at in the research labs, also being developed by companies to try and squeeze out these last few percent from the silicon cells. And obviously, a key part of this work is looking also at manufacturing, trying to make manufacturing as cheap as possible. There's been fantastic success in that, obviously, over the years. The costs are now incredible. PV is now one of the cheapest energy sources you can find, thanks to these great developments that have been done over the last decades. And I think we have to recognize the great work that's been done also by Chinese companies in particular in this arena. Although a lot of research has been done on a global level as well. So we're trying to squeeze out a little bit more we can, but we're kind of reaching the end. Sustainability is another point as well. Obviously, silicon is very abundant. The glass that protects the modules are very abundant, but there's other elements which are quite critical. For example, silver is a big one. That there's a lot of work going in research to try and reduce the amount of silver that is needed for the contacting. So next slide, please. Then we have topic 2, which is focusing on basically everything that's not silicon, if you like. The big thing at the moment is perovskites. There's a huge amount of research going on in this area of perovskites. Perovskites basically refer to a type of crystal structure, which has been found to be very, very excellent at producing electricity from sunlight. Lots of different chemistry going on. People are looking at all sorts of different ways to make it more efficient and have a longer lifetime. So it's very efficient. It's a thin film, so it's not crystalline like silicon. So it is susceptible to perhaps issues to do with degradation. This is a big area of study as well. But one interesting concept is to put perovskite materials on top of a silicon cell and make a tandem device, which can improve efficiency, but also the crystalline material will provide a good solid base for the perovskite material. So it's a very promising area of research. But we also needn't forget there's other technologies that have been discussed for many, many years, CIGS, cadmium telluride, organic technologies, which are also very, very promising, and research continues in all of these. And as well as a lot of novel concepts that people are trying to develop, which might make some crazy breakthrough and find something spectacular. And there's always people working on these areas, such as quantum dots, up conversion technology, lots of things like this. So next slide, please, John. Then we have topic 3, which looks at photovoltaic modules. So basically, you make a cell, then you've got to turn it into a module, which can be put in the field and have a lifetime of hopefully up to 30 years and beyond. So there's a lot of work goes into how you assemble this. All the materials are needed to make sure it has a reliable lifetime. Make it as cheap as possible, clearly. Then another topic that's come up recently in the last few years, which is still drawing a lot of attention, is the idea of bifaciality, where a cell can be made to accept light from both sides. And this way you can harvest more light in certain scenarios where you can also take the light reflected from the backside. Or, as we'll see later, it can be useful in vertical configurations, for example, in agri-PV. A very, very good, promising development here. And in this topic, obviously, the performance of the modules in the field is very important. Standardization, so you can measure them correctly. Also here, the circular economy is a big question. How you can make modules so that they can be easily recycled in the future is a huge point, because obviously photovoltaics wants to be a sustainable technology. So it's very important that this sustainability is built into the module when it's designed and manufactured, and we don't try and deal with the problem down the road. So we try and anticipate any issues you might have with the circular economy later on. So next slide, please. Then we move on to the topic 4, which is photovoltaic systems. So we go here from looking at the solar resource that we have, system design, how the systems perform. Operational maintenance is very, very important. When you have particularly very, very large systems of multi-megawatts, you cannot go around looking at these one by one to try and identify issues. You need to be able to do this remotely. So there's a lot of work going on with remote sensing, also sometimes using drones, for example, artificial intelligence to analyze the system performance. And with very, very large systems, this is really critical because we're talking about having terawatts of systems out over the next decades. And it's really important that we can maintain these in the top form of operation with the minimum of manual interference. Very, very important. So digitalization, AI, as I said, is very, very important. Then another part of this is also the applications where we can put the modules so we can try and avoid land use issues as well. Very important. So we're looking at floating PV is a big area. Building integrated PV has been also for a long time, putting PV on the roofs, on the facades of buildings, integrating them in very clever ways. And agri-PV is another area that's getting a great attention at the moment, where you can even boost the agricultural production by having PV modules. So you don't even necessarily reduce the agricultural production, you can even boost it in certain climates. So it can be a win-win for the farmers and for society. So then the final topic is topic 5. And this is called photovoltaics in the energy transition. So this covers all the bigger things, and I guess it's getting more close to where we are today in terms of how do we integrate all these systems, all this electricity we're generating from the sun for free, effectively, almost for free, and how can we integrate that into the grid and have a future grid which is stable and reliable, which can take in obviously PV, other non-dispatchable sources, can be wind, can be hydro, different things like this, and put them all together into a system which is going to be intelligent, smart, and reliable, and cheap in the future. So we look at lots of different areas here. Sustainability is also a very big aspect of this work, to make sure that this new system is going to be fully sustainable and clean, environmentally clean. And then finally, there's some questions about society as well, because obviously you need to have societal benefits for this huge, big energy transition we're going through, and we need to make sure that everybody wins in this transition. So then if we can have a look at the following slide, please, John. I guess the PV, what we have now is panel discussions. Okay, the panel I reversed the order of those slides. We have some panel discussions, which I can really indicate where some of the key issues are at the moment. So I won't read this all out, just very quickly. Questions about the reliability. When you introduce new technologies, we need to be sure that they are fully reliable, to make sure that they can be invested in. The manufacturing, let's say the geographical balance of the manufacturing ecosystem is at the moment very skewed to certain regions in the world, and there's big questions at the moment about whether this should be perhaps diversified to different regions, particularly from our perspective looking at Europe. So we're talking about what options does Europe have to try and grow its own manufacturing ecosystem. And then the final one is looking at challenges and opportunities of PV. And here we're looking at societal aspects, like I mentioned, but also artificial intelligence. And it is also mentioned this question about energy storage as well. And that brings us to what we're talking about today. Then the next one, we're looking at plenaries. I think the plenaries are a great opportunity to hear about specific technological developments, but which are directed at the audience, at a bigger audience. So they go into less details, but they try and give you a picture where we're at. So these plenary talks, I won't go into details, but they give a highlight of what we're talking about. We're talking about manufacturing, putting PV into the field and applications. One focus is on this perovskite silicon tandems. How can they be commercialized? How can we be sure that they're stable in the field? And then the final one, again here, flexibility and sustainability, brings us, I think, nicely to the topic of the other theme we have on this webinar today. And then I think I would conclude with the last one is like just a very quick summary. Where are we heading? Okay, so the key questions: how much more can we squeeze from silicon? What's likely to come next? Perovskite is looking like a big contender to be the next one. After that, maybe we're talking about maybe a time frame of by the end of this decade, perhaps. Then how can we operate all these multiple terawatts of systems out there? How can we make sure they work correctly and reliably? Where are we going to put them all to reduce land use? So we're trying to put them in smart places, as much as possible. And then how do we integrate into the energy system? So again, the big questions about dispatchability, storage, all those questions, sustainability, very big, and the societal aspect. So these are the big topics we're talking about at the conference. And then finally, in the last slide, I would just like to thank you for your attention and hopefully maybe see some of you in Bilbao in September to learn more about the things I just highlighted. Thank you very much.
Thanks a lot, Robert. You were in your last slides launching some questions. I will launch one to you that I hope you can reply in 30 seconds. From a research perspective, what do you consider the most critical barrier to innovation in PV technology today?
Well, that's a tough question. I mean, first of all, I'd like to say that we see a lot of innovation. So we don't have, I mean, there's a huge amount of innovation going on. People are still working on silicon big time to try and squeeze this last bit of efficiency. We've got a huge amount of innovation going on, this new up and coming technology, which is perovskite. We see PV modules being put into all sorts of scenarios on vehicles and on fields, on roads, on rivers, there's a huge amount of innovation going on there. However, I guess I would say that, let's say, particularly from a European perspective, not having a big ecosystem for the manufacturing side, I think is putting a big restriction on the research, because it restricts the money available and the prospects for turning some research into something, into a product, like say. So that's certainly, I think, from the European perspective, is causing some concern. I think we need some strong political ideas into trying to get that back on the road again, and I think that will also boost the research perspective from the from the European perspective particularly.
Thanks a lot, Robert. We will have time to further discuss in the second block. Now I will start introducing our next speaker. Silvestros Vlachopoulos will deliver a presentation with title Overview of Energy Storage Market. Silvestros is a senior consultant at LCP Delta, where he leads the energy storage research service and the StoryTrack database. With over a decade of experience in the energy sector, including roles in project development and consultancy, he brings expertise in distributed generation, electricity networks, and sustainable energy systems. Silvestros, the floor is yours. Thank you.
Thank you, John. And hi, everyone. Yeah, thanks for joining. As John said, I will present today some key highlights from the storage market and how is it going in Europe. Hopefully trying to tie this up a little bit with solar PV, with some data that we have. I'll just try and share my screen, which should be going okay as far as I can tell, but please let me know if it doesn't. So yeah, I'll try to summarize as much as I can in 10 minutes what is happening with storage in Europe. The results that I'm going to present are largely based on a report that we do with collaboration with EASE every year. At the beginning of the year, we call it the European Market Monitor on Energy Storage. And effectively, this report just tracks what is happening on the market. We also have an updated view every year on how fast the market is moving. So we sort of provide a forecast on a country level with how much storage there is going to be in the system by 2030. But let me get to the numbers themselves and start the story. So overall, currently, this is the status of play right now for the energy storage market in Europe. There are 89 gigawatts of installed capacity across different technologies. And here you can see the mix-up on the left-hand side. Most of this capacity currently is pumped hydro storage, which is not really a surprise. This is the legacy technology that has been installed since many decades ago. Currently, there is some still new developments happening in pumped hydro storage and some new projects, but overall, it's growing relatively slowly if you compare it with the other emerging technologies. And when talking about emerging technologies, really the key one is electrochemical storage. This is the new comer in the space, where we currently see 35 gigawatts being operational by the end of 2024 in Europe. And these can be broken down between front of the meter and behind of the meter storage. As you can see, behind of the meter storage is currently a bigger market than front of the meter storage. There are some reasons as to why this happens, and we can explain more about it. And then you have some new emerging technologies that are lagging versus the other two groups, let's say, such as large-scale thermal and other storage technologies. Other in this context would include things like flywheels or compressed air. Obviously, flywheels also don't contribute a lot of power anyway, so we wouldn't see big numbers from them anyway. And then you can see how this looks like the mix, if you want, across Europe on the map on the right-hand side. The darker the color, the more capacity a country has in terms of storage. So this means that, for example, you have countries like Germany or Italy that have pretty much a decent capacity of all of these technologies, a little bit of pumped hydro, a lot of electrochemical storage behind the meter and front of the meter that have the darkest color. But you also have countries that have a little bit of, a small amount of these that have, let's say, a relatively dark color. I guess an example could be like someone like France, for example. Now, going forward and discussing about the electrochemical storage market, which is the one that is growing more aggressively. As I mentioned before, behind the meter storage it has a larger capacity at the moment. However, the dynamics are shifting. Our view is that front of the meter storage will surpass the capacity for behind the meter storage by 2030. You can see here the results of our forecasts. And in terms of what else has happened already in 2024, behind the meter storage saw a decline, whereas front of the meter saw market growth in 2024. Now, some of you may think why this is the case. Why is one sector seem to be performing better than the other? Well, this could be attributed to many reasons, but I've picked up a couple here. For me, one thing that is important is the different types of investors. So with front of the meter storage, we're talking about big utility scale plants. You have different types of investors, different access to capital. They can more or less understand better the intricacies of the new technology and invest in it. On the other hand, for behind the meter storage, you basically have to rely on your average consumer, which is not very well aware of these things and obviously has less easier access to capital. But also, one thing that is important is that at the moment there are some really strong market signals for front of the meter storage, and there's a lot of support that has come over the last couple of years from a European level on front of the meter storage, and this is going to essentially bear the fruits in a few years' time. Moving onwards, just a quick snapshot of what is happening in some market segments. So residential market, as I said, the market declined in 2024. This is mainly because there was a reduced deployment in Germany and Italy, which are the key markets for residential storage in Europe. We also have the removal or reduction of some important subsidies in some of the key markets, which also contribute to a further decline. Overall, the narrative is that now energy prices are not as strong of a driver as they used to be in the period of 2022-2023, which resulted into a very big market growth. At the same time, you have consumers who are pressured by inflation or higher borrowing and cost that effectively affects their decision to invest into a technology like that. Going forward, we do expect the market to eventually recover and sort of continue in a growth trajectory. I think what is important to highlight in terms of drivers here, I highlight the dynamic tariffs and kind of the changing remuneration for solar PV. Essentially, the more sophisticated and the more tied in your solar PV remuneration is to actual energy markets, then this creates an incentive for the use of flexibility in the forms of battery storage. So these two, I think, will play an important role in the growth of the market towards the end of the decade. Now, front of the meter market, here the picture is a bit more complicated, as you can see also from the graph. One of the key developments recently is the billions of euros that have been spent in support schemes that incentivize the deployment of this technology, which basically are going to result in a market peak in 2026, as you can see. So this is going to be when most of these projects will get connected. In terms of other trends, this is a bit cross-cutting, but cheaper batteries are essentially making projects more viable. So this means that markets that, let's say 3 years ago, weren't as attractive for storage, now just because of lower capex, things are starting to become more viable. The cheaper batteries also have a side effect that the scale of projects increases, so they basically projects become bigger and bigger. And another point is that the energy markets are currently looking very volatile, and a lot of this capacity that you see here is driven by capacity market contracts that provide some revenue certainty that is important to make a project bankable. So a key example of a country like that is Poland, that had very attractive capacity market contracts and that have played a big role into feeding its pipeline. However, that's highlighting also some of the challenges that remain. This is a huge growth. The sector is going to face some difficulties with the grid connection bottlenecks. Maybe a project is connected, but it doesn't mean that the network operator will be able to keep in touch with the huge volumes that are planned to get online. There are also issues with project financing, delays connected to EPCs or supply chain, just because of the scale of what's coming up in the next 5 years. But overall, the picture is let's say very positive. And then I have a couple of slides here before I finish that try to tie in storage with solar. So I mentioned before about the kind of residential storage. Residential storage is, let's say, almost always co-located with solar PV. So this means that typically a good market for solar PV should also be a relatively good market for batteries. Obviously, regulation plays a role in that. For example, if you have net metering, you might have a lot of solar PV, like the Netherlands, but not a lot of storage. But it is something that we see being increasingly more and more co-located. If you look at the whole fleet of Europe, our statistics show that around 20% of the existing base of batteries, of solar PV, installation has a battery with it. And currently, if you just look at 2024 number, this figure is closer to like 40%. Again, on average across Europe, which is quite a big percentage. And then finally, in front of the meter, this is again co-location, let's say, with other technologies becoming more and more common. Also increasing, I guess, as the market scale increases, as I showed you in previous graph. But here you can see some of the co-location trends. Solar PV is increasing with the blue line, as you can see, but so is wind. Let's say the drivers for both should be the same. I guess what would change would be the market characteristics, let's say, that might dictate where you would collocate, in which country you would collocate with wind or solar. We also have some collocation with some traditional plants that there isn't, they aren't really interacting as much. But also just highlighting here on the right-hand side, some of the countries where we see most of the collocation happening. Germany, Italy, Great Britain are the main ones, but those are also, let's say, the main front-of-the-meter markets for storage. So it's not really surprised that we see them relatively high. But also like highlighting, for example, Bulgaria that installed quite a decent amount of capacity collocated with solar PV already in 2024. And yes, that was my presentation for today. And thank you so much for your time.
Thanks a lot, Silvestros. Really interesting presentation. Nice overview. If I may launch a question to you, I will underline or keep on underlining a bit the innovation perspective. Just in 30 seconds, please. Are there emerging technologies that you believe will gain market share in the next 5 to 10 years?
Yeah, well, that's a good question. Again, difficult one to answer in a short time frame. I would say that Personally, I think that there is a big scope in increasing share of thermal storage. This is basically an unexplored space at the moment, but it is going to be important to decarbonize industrial heat in the longer term. So this is one of the technologies that I could expect to see more of going forward. And then obviously highlighting things like the long duration energy storage technologies, which is a large group, I know, but it's hard to pick one particular one in that context. But this is going to be, let's say, the next step for energy systems after the first influx of short duration BESS, let's say. Then is obviously a lot of innovation on the electrochemical side, but this will get us into an even longer discussion on the different chemistries that can be available.
We might have time later on. Thanks a lot. Our next speaker of the day is Grazia Barchi. She will be delivering a presentation with title The Role of PV in the Future Energy System. Some words about Grazia. She's a team leader and senior researcher for grid integration at URAC Research. You can see it already on the screen. Her work focuses on distributed energy resources, including photovoltaics, storage, and electric vehicles, as well as their integration into power grids. She's a prolific scientific author and active member of several international technical committees, associations, and technical platforms. Grazia, the floor is yours. Thanks a lot.
Okay, thank you, John, and good afternoon, everyone. I hope that you can see my screen, probably yes. So thank you for the opportunity to speak today on the evolving role of photovoltaic in the future energy system. I'll briefly touch on the current status of PV and the trajectory of the decarbonization scenarios, and also the possible challenges and solution integration of an electricity grid. So let's start with some number. Here you can see the evolution of cumulative PV capacity over the last year. You can appreciate that the exponential evolution of PV, we took more than 40 years to reach the so-called terawatt area, but we doubled this quantity just in a couple of years, especially due to the contribution of China that has nearly 50% of cumulative worldwide capacity. If we look on the annual PV installation, you can see that the trend is similar, and in my opinion, it is also relevant to see a little bit the segmentation of the last year new installation, because this is also related to the number that we saw related to the storage, for example, at prosumer level. And we can see that 61% is still utility scale, but also there is a big contribution from the rooftop PV. And if you look to the number specifically, we have a larger number of small scale PV, but obviously the capacity is lower. All the net zero energy and decarbonization pathways give to the PV a fundamental role. I want to say it will be one or maybe the driver in terms of renewable energy source for the net zero energy transition. Here I reported some of the most famous scenarios, and please especially focus on the ones that is related to the 100% of renewable energy developed by the Youth University, where we consider 63 terawatt peak of PV. So the pathway is still long. But even though everyone agree on the fact that PV generation will be one of the driver for the energy transition, however, how the PV generation capacity foreseen for 2030 and 2050 scenarios will be integrated in the electricity grid is less obvious. In a European project called Trust PV, we tried to do an exercise and a study that want to be, I want to say, exhaustive, but the idea was to link the target, the energy scenarios, and to the grid planning in order to have at least a quantitative and quality idea, which is the situation actually. I will show a little bit the work that we perform. We've selected 5 European countries, the ones colored on the map, and we found the optimal energy mix by using the ePlanner tool developed by our energy system group in the Institute, which combine an energy model simulation tool, the energy plan that is quite famous, developed by the University of Aalborg, with the multi-objective evolutionary algorithm. We solved the multi-objective problem by minimizing the energy system cost and the CO2 emissions, and the result led to the multiple optimization solution distributed over the Pareto front, as you can see by the animation. Then, in order to evaluate the impact at the distribution grid level, because that one was our focus, we needed to convert the PV penetration in energy into the power, and this plot represents the all the value of the Pareto front in a box plot for the 5 selected countries that are Italy, France, Spain, Netherlands, and Sweden. To appreciate the validity of the achieved results for the 2030 scenario, we report with the red star also the value indicated by the ENSO-8 scenario, and as you can see, they are completely within the box plot that we obtained. After that, to evaluate the impact of PV system on the grid, we employ the hosting capacity assessment. For those who are not familiar with this concept, essentially the hosting capacity refers to the amount of PV, or I want to say any other distributed energy resources, that can be integrated into a given distribution grid without affecting its performances in terms of electrical quantities, that is, voltage, current, thermal rating, and power quality. The methodology that we adopt consists on a detailed power grid model. We selected the performance indices that in our case were over voltage, line overloading, transformer overloading, and we iterate using a probabilistic approach to run the power flow computation. Once the electric quantity are compared with the performance indices, if the performance indices are violated, we reach the hosting capacity. Otherwise, we increase the PV penetration level. Essentially, the results, the method has been applied to 3 European reference distribution grids extracted by a JRC report, which collected information about grid data with a survey over 190 DSOs and elaborated some example of a European distribution network for research purposes. Then we consider the average values of the PV penetration found in the energy scenarios. We use the pointer, it's easier. And the results that we achieve for the low voltage urban, low voltage semi-urban, and medium voltage rural grid that are reference grid, so not related to any geographical, I want to say, reference. And the message was that for Italy, Spain, and Netherlands, the energy mix and the housing capacity are closer, while for Sweden and France, that is not, that is not true. But this doesn't surprise, because essentially France and Sweden does not base their energy mix on PV generation. This methodology was based on the computation of hosting capacity in steady-state mode. That means without consider any kind of flexibility, storage, control from a smart inverter, and so on. So this is underestimated. This means, but this exercise was useful to understand that the future planning tool should incorporate also some flexibility. And the flexibility will be one of the possible solutions to increase and allow, and I want to say enable the high PV penetration. That is the target that we need for the different scenarios. I don't want to spend too much word about this because it's a quite general one, but essentially, as you can probably know, the flexibility can be provided by different sources from demand side, from grid side, and the idea is also to defer the possible grid reinforcement in a short time. And obviously, it is provided by storage and sector coupling. I just wanted to report a couple of examples, the quantitative one, that give you an idea on this effect. The first one is related to the possible flexibility provided from demand side and sector coupling. Here we develop a methodology to minimize the net load peak at the transformer level of a secondary substation by considering a feeder that has a different penetration of photovoltaic and 60% of electric vehicle. And in the 3-bar chart that you can see, we can analyze, we can appreciate the different behavior in terms of voltage level violation for 3 different scenarios. So the presence of only PV in yellow, the presence of electric vehicle but without any smart charging or vehicle to grid approach, and in red the vehicle to grid approach. And you can see how the smart charging and vehicle to grid approach essentially reduces significantly the limits of the voltage level. Then another example is the ones to reduce the flexibility requirement. That means from one side we need flexibility to, I want to say, counterbalance the variability of high PV and so PV and wind integration. But on the other side, if we act at power plant directly level by coupling the PV with smart inverter and power plant controller and battery, we can use the generation split. That means firm some of the generation and inject the other into the grid. In this case, we enhance the hosting capacity because essentially we decrease the variability. In this specific study, we consider that 30% of the production is used for a renewable energy community and the rest is injected into the grid. And there's data coming from a techno-economic optimization considering the actual battery cost. So key message from my short presentation are essentially that the energy scenarios indicated that the PV technology will be fundamental for the energy transition. In the meantime, we need to modernize also some planning and operation practice at the grid level and to unlock the flexibility that is provided by complementary technologies. The role of PV will be not only and merely in the future as a generator, but it will become an active participant in the future energy system. So, thank you for
Thank you, Grazia. I'm not sure if we have lost you. I am not sure if I can hear you.
Okay, I'm here.
Now I hear you. Now I hear you. Perfect.
Okay,
yeah.
good.
Really, really short. Thank you once again for your presentation. Really short question for you. You were referring before to hosting capacity and the concept. What is the current state of hosting capacity assessment? Is it a common practice?
Okay, that's a good question, even though because I mean there is not a standardized method to assess the hosting capacity, and this is a practice that at grid operator level is done, but now the development is that some of grid operators also publish a kind of hot maps to show the hosting capacity over their grid, and this could be also useful, for example, for producer and to facilitate the integration and installation. But sometimes is not so clear the methodology to assess this, because it depends if you consider, for example, steady state behavior, and in this case you underestimate, because we know that the behavior of PV, wind, or also electric vehicle is variable and depending on the time, so we need to know the profile and so on. So it is still a practice that is under development, but is becoming more and more interesting tool, not only for who operates the grid, but also for prosumers and for producers.
Thank you, Grazia. We move on quickly to the next presenter, who is Ed Maculloch from Tesla, who will deliver a presentation with title "Ensuring Energy Security with RES, energy storage, and grid forming. Some words about Ed. Ed is a new market entry lead for EMEA Tesla Energy, where he supports Tesla's mission to accelerate the transition to sustainable energy. He has extensive experience in renewable and distributed energy technologies and holds multiple patents. Licensed professional engineer, he earned engineering degrees from Stanford University and the University of Virginia. Ed, the floor is yours.
Thank you. Yeah, thank you everyone for your attention today. I wanted to let's see slides here. So starting off just with Tesla's mission, our goal is to accelerate the world's transition to sustainable energy, and we are participating in that transition in a number of different ways. Tesla is best known for our first product, the electric vehicle, which continues to be our primary product. But people in this forum are probably also aware of our energy storage business, which is roughly 20% of the business today. And I wanted to share our experience on the industrial energy storage side, particularly as it pertains to grid resilience. So this is the map of the deployed energy storage today. In the light blue is a power pack, our legacy product, and the dark blue is Megapack, our current offering. As others have noted in their presentations, we've seen a transition or shift towards larger utility scale projects over time. And currently we're at just over 27 gigawatt hours of operating battery storage projects across over 2,000 projects in 60 plus countries. And we're expecting that to continue to grow. You can see the annual manufacturing capacity is up to 80 gigawatt hours. So we're expecting additional demand in the future. So I think one key transition that we're seeing going on today is the transition from traditional generators historically providing grid resiliency to batteries and other inverter-based resources operating that in the future in a clean way. And while traditional generators have done a pretty good job of that historically, there are a number of limitations when it comes to trying to do a carbon-free grid. So I wanted to share our experience at the utility scale with grid forming projects. This is a subset of the utility projects, which are primarily operated in a grid following mode per historical regulations around inverter-based resources. Our experience with utility scale on grid projects started in Kauai back in 2018 with what today is a relatively small project at 13 megawatts. Since then, Australia has been a leader, and Hawaii has continued to expand their grid forming projects. And so we have over a gigawatt operating today, and a healthy pipeline of additional projects beyond these that are currently in operation. And I think there's still some, I guess the story hasn't gotten out to everyone that grid forming batteries are currently in operation and effective at the utility scale. So really wanted to take the opportunity to highlight that it is a well-proven technology at this point. Wanted to share a specific example. I think a number of people are probably familiar with the concept of inertia, which historically has been provided by the rotating mass of synchronous generators or synchronous condensers. And the primary advantage of that is to slow the drop of after a contingency event, such as a trip of a generator, to slow the rate of change of frequency, and that during what's shown as the arresting period here, following the contingency. And slowing that rate of change gives time for other devices to detect the reduced frequency and respond by primary and secondary frequency response, and rebound and stabilize and recover the frequency longer term. This is a graph from one of the Hawaii projects called Kapolei Energy Systems, or KES for short. In February of 2024, one of the generators in Oahu tripped offline, which created a sudden shortage of generation. You can see in the graph to the right that the arresting period started as soon as that generator tripped, and the frequency reduction started at the same time, and the battery that battery is in a grid forming mode, and injected power, inertial response power, immediately following the contingency event or the generator trip, and continued to provide that power until the frequency dropped to 59.4 hertz, which is when additional power kicked in from the fast frequency response, and that was within a quarter of a second, 250 milliseconds. So this event, I think, is a good illustration of a utility scale outage that was avoided by a battery providing both inertial response and fast frequency for frequency recovery. This is a quick comparison showing how a grid forming battery stacks up relative to other sources on the grid. A synchronous generator has a lot of the same capabilities. Harmonics dampening, or dampening in general, is more limited from synchronous generators because it's either provided by PSS or damper windings, which both have limitations. And fast frequency response is limited by the governor's ability to react to a change in frequency. And of course, energy shifting. A synchronous generator can't store energy in most, depending on the prime mover, but most conventional plants wouldn't have that capability. And then black start is a capability that batteries are well suited to, given the large amount of stored energy, but only some synchronous plants have that capability. And then these additional assets have a subset of the capabilities of a synchronous generator, conventional synchronous generator. So yeah, we're seeing this transition really happen around the world. I mentioned Australia and Hawaii, but in addition to those, we're seeing it in ERCOT in Texas, EirGrid in Ireland, IEEE across the US, and NESO in the UK has been they've been ahead of or leading the transition to grid forming in Europe, or on the continent. And yeah, finally, just wanted to point out the speed of battery deployment can be quite fast. We deployed a large battery in Hawaii several years ago, and within 100 days. It's a modular, pre-assembled, pre-tested product that gets shipped and dropped on site, wired up, and is ready to go. And batteries are really the cleanest way to continue to decarbonize the grid, reach the targets for renewable generation at the grid scale. Thanks for the time today. appreciate your attention and feel free to reach out with any further questions.
Thanks a lot, Ed. I will start. I have that privilege. You were mentioning some experiences in some parts of the world, and in one of your slides, you were mentioning as well the TSOs. So, in your opinion, what lessons can European TSOs can get from these other experiences and regions regarding the role of grid forming batteries?
Yeah, thank you for the question. I think it's really a matter of identifying best practices from across the globe, and really in two categories. I think the first is market design and setting up incentives for batteries and other resources to provide grid forming capability. I think there's some limitations around a universal mandate that could, and I think that a incentive-based approach is more likely to succeed and avoid pitfalls with trying to force everyone to do it. I think the second major bucket is around certification or validation. Sort of a fundamental challenge with inverters that you can look at an engineering drawing of a synchronous generator, and a power systems engineer could predict its behavior pretty accurately. But with inverters, it's really comes down to the firmware, and so being able to validate that the firmware and the hardware combined together do what they're supposed to do in the actual moment of need is something that has been figured out in a couple of different places, or different approaches have been taken in a couple of different places. I think the ongoing validation approach in Australia that AMO's introduced is a good example of how you can ensure that actual behavior is going to match the simulation. In Europe specifically, the RFG2 is going to mandate grid forming for inverters type B and above in the next few years, and so individual TSOs are going to need to implement their programs to ensure that they're making the best use of that.
Thanks a lot, Ed. We will move now into the second part. Sorry, we are a bit late, but we hope that you will stay still a while with us. I will hand over to Jacopo Tossoni for this second part, the pure panel discussion. I will introduce very briefly. Jacopo serves as head of policy at the European Association for Storage of Energy. He leads the association's advocacy efforts in the field of energy storage, with a particular focus on electricity market design and energy security. Jacopo, please, the mic is yours. And the
Thank you so much, John.
Thanks
Thank you, everyone. And thank you also to the attendees who are dropping questions in the Q&A section of Teams. We're going to get to your questions. I've seen quite a few good ones. So keep them dropping and we'll come to you. But now let's take a few steps back. Let's go back to Robert and Grazio's presentation. We've seen now a few solutions with Ed to address the issue of maybe security supply and so on and so forth. But from your perspective, what are the bottlenecks that are limiting reaching high penetration of PVs in the future scenarios? Robert, Grazia, whomever likes to go first, goes first.
Grazia, do you want to go first?
Okay. I can go first. Thank you for the question, Jacopo. Well, I mentioned some of them. For example, this limitation of the hosting capacity, especially at the distribution grid, is one of it, because essentially at the moment the distribution grid are not designed, for example, to have to manage the reactive power or the voltage rise that the PV can create. But I want to say that even and perhaps beyond the technical one that can be mentioned, like the limited capacity, the thermal rating, and so on. So essentially related to the infrastructure, if we look to the grid integration side. Another point that coming me on mind are also the, for example, permitting phase that takes a long time at the moment. For example, in Italy, we have the situation that they are in really delay. There are several requests to connect, but so we need to understand also how to make faster this process, not only from technical point of view that can also solve with the nice technologies that we saw from Sylvester's and Ed, but also from the, I want to say, regulation and point of view.
Robert, what do you think?
Yeah, well, basically coming from the perspective of the PV side, so we've come from, and since the 20 years or more I've been working in the area, we've gone from, you know, a dream to have some product that can be put out there and work and be cheap enough. Now we've arrived at that point. It's now we have PV modules which are really cheap, can be put out in huge quantities. So we're kind of the victims of our success. We're now reaching the point where we've said, whoops, we've got so much PV out there that we're starting to find that the grid operators are saying, hold on a minute now, we don't know if we can cope with all of this. And also you find systems having to be curtailed as well. So you get moments, sometimes it's been reported in certain countries at certain times where you've got renewable energy is producing, you know, 100% of the capacity of the entire system. And, you know, this starts to reach a point where it's not easy to manage anymore. So I think what we've identified from our side is, okay, we need a smart grid, and with some forms of storage is going to be needed. Now that doesn't mean batteries necessarily. Despite that, I mean, okay, I mean, what Ed has reported on is fantastic. What the battery side can do, but I mean, I think there's lots of different solutions out there that need to be worked on all together. We're not going to be able to have one solution only. Grazia mentioned also electric vehicles. I think it's very promising the way you can combine that. Also self-consumption, power to X, very important. Hydrogen is something we didn't hear about today, but that's a big topic that's been mentioned a lot, is hydrogen as a vector for storing energy as well. So it can be produced in large quantities when the sun is shining, and then it can be and the wind is blowing, and then it can be turned into something else when it's needed. So these are all parts of the thing. So from our community, specifically in the PV side, this is something we have a certain amount of expertise in, but not probably everything we need. So I think that's what we're trying to do here, is reach out to all these different communities working in all these things, and we need to work together in a holistic way to make a system which is going to work for everybody.
Perfect. So you mentioned a very important concept and a very important challenge, which is curtailment. You already maybe highlighted possible solutions to that. Grazia, Ed, is there something else that you think attendees should know, attendees of this webinar should know? Is there some specific strategy that you know, should be taken into account to reduce or limit curtailment as much as possible?
One point that coming me on mind that was not touched yet is, for example, to improve the forecasting of PV production. Better and more accurate is the forecasting of PV production, and lower is the curtailment that we can act. And if we combine the accurate PV power forecasting with also storage and proactive curtailment, we can also assess a system that can well integrate with minimizing the losses and the waste of energy that we can have, for example. This is something that was not mentioned yet. And then Robert mentioned obviously other aspects related to possible sector coupling or demand that can match more the production.
Okay, and Ed, from your side, you were showing before a bunch of projects across the world from Tesla. We're doing quite a wide array of services. How does curtailment and maybe inertia, which was the topic that you're covering, fit together? Is there a project able to do both things, or different projects for different objectives, for different challenges? And investors, feel free to jump in as well if you after that.
Yeah, I think the way I think of it is that storage is really required for the energy shifting for intermittent renewables, both solar and wind. Since production is variable, some degree of energy storage is required to ensure that that energy can be available at the time you need it. And whether it's co-located or market-based, and I think that just having more storage, it enables that, or is required to enable that. And then I think inertia is almost like an ancillary benefit available from storage. It's a system stability need. I think traditionally provided by synchronous generators, but can be provided by inverters, particularly battery inverters, and it doesn't need to be provided by synchronous condensers, which has been kind of I think the traditional utility response to inadequate inertia. But since it's an unnecessary expense or capital asset on the grid, since we're going to need the storage, and the storage has that capability.
And if I might add something, Jacobo, is it's almost in the nature of batteries to, let's say, provide different services where they are like their let's say the revenue stack tends to be complex anyway, and it gets more complicated the more advanced the markets are and the more competitive. So I would say that things like you mentioned, for example, projects combining something like congestion management with inertia services or frequency services broadly. This is a potential direction. However, right now this is not something that is happening to any big extent, as far as I know. Maybe there are like one or two like flagship projects that we can point at, and there are like platforms where you can procure congestion or whatever, but typically you don't see them matched up in a single project yet. Let's say if you look at what's happening on the market.
Okay, and maybe combining a question that I have with a question from one of the attendees, how is usually procured inertia across Europe, and maybe what are your expectations in the next few years, starting with you, Sylvestris?
Yeah, well, I think like traditionally, let's say inertia isn't really procured. It's almost like, because it was an inherent capability of traditional thermal generators and nuclear. So I wouldn't say that there are like many markets available. I think one interesting outcome that is about to happen is Germany, who's going to introduce an inertia market in 2026. And this is going to be an interesting one. Essentially, they're going to give some stable revenues for, I think, contracts ranging from 2 to 10 years for whoever is going to provide it. Obviously, this includes also synthetic inertia, the type of that Ed hinted to. But yeah, I guess this is kind of the current state of play. Let's say it's not procured, let's say, much on a market basis. Perhaps there are like pilot projects that provide it. There is one in Scotland, in Great Britain, for example. I think the German example is one that it's looking really interesting for the imminent future, let's say.
Perfect, thanks so much. Ed, beyond the how to procure it, the size itself, do you have an understanding of what's going to be the market for inertia service in the next few years? For example, are we talking about megawatt? Are we talking about gigawatt? Are we talking about hundreds of gigawatt?
I think the most recent study I've seen was one commissioned by the European Commission and performed by Artelis, which projected around 600 gigawatt seconds of inertia to handle the system split scenarios that they analyzed. So I think extrapolating with some typical assumptions like a 10-second inertia constant and typical ratios, that would be around 40 or 50 gigawatts of nameplate battery power required to provide that. So it's within the their target was their study was assessing by 2030. So I think that lines up pretty closely with the projections for the market.
And I suppose an even more dramatic growth for 2040 and 2050 as the market, as renewables get further deployed. I suppose also the inertia market is also going to increase, and the inertia need is going to increase. Okay. Before we conclude, because we already are 3 minutes late, of course, the big topic of the past few weeks, of the past few months, has been the blackout in Iberia. Here, we do not know yet what has happened. So we do not want to comment too much until we have all the pieces of the puzzle on the table and we understand exactly what happened. But looking maybe at the Spanish government report that came out a few days ago, is there something that caught your eyes that you thought, okay, this is particularly insightful, maybe this is a lesson to keep in mind, or something of the kind? Whomever wants to jump in, the floor is all yours.
I guess if I might start, Jacobo, I guess some thoughts, not necessarily on the document, let's say. I think we can all agree that having some more flexibility in the system would have helped. So obviously, more storage, more use of demand side flexibility overall, that could have helped. I guess two things that I want to highlight is perhaps one is how you run, like how system operators run their worst case scenarios, because I think in the case of Spain there was a big loss of power capacity, but also like connecting a bit to the points I made before. What are the policies or the market rules for any services that you can provide? For example, potentially Spain could have benefited from really fast-acting frequency products if they were available in the market. That's my 2 cents on it.
Okay, go ahead.
Yeah, I guess another thing that stood out from the Spanish report was the inadequate voltage control in the system. And I think both PV and battery inverters can provide reactive power for voltage control very quickly and without the limitations associated with AVR on a conventional generator. So I think those are both, that looks very promising for having renewables and inverters take on that role longer term. I think another thing from the blackout is the recovery, which I think black start capabilities from a battery would be well suited for any grid recovery scenario.
Okay, perfect. If there's no comments from Robert nor from Grazia, guys, thank you very much. Attendees, thank you very much. I've seen quite a few questions in the chat related about the recording of the slides. Yes, we're gonna share them after the meeting. You also get a few contact details of the few speakers, so feel free to reach out to them individually. I think today we got as a key takeaway is that, well, we're gonna have further and further renewables into the system. The economics are great. There's been a dramatic increase in penetration. There's gonna be some challenges, or there are already some challenges, but hopefully there is both the technical and political will to intervene to maybe ensure that from a system need perspective, from a security of supply perspective, we're able to provide in terms of services what the system needs. So thank you very much, attendees. Thank you very much to the speakers as well. It's been a pleasure. And if you have any questions, do not hesitate to reach out to us. Thank you again. Bye-bye.
Thank you, everybody. Bye-bye.
Bye-bye. Thank you.
Right. Thank you.